In this video, I want to take another look at solving differential equations with Power series. In this case, I'm going to do a non-homogeneous equation. But like the last one, I am going to do one where we have another method for solving the equation so we can double check our results. Um, Here we go. This is the second order non-homogeneous equation I want to do. It is constant coefficients. So I could do this in the old-fashioned way of saying, hey, let's assume the answer looks like e to the rt, or in this case, e to the rx, because we're in chapter 5 now, and x is the variable instead of t. So you get the characteristic polynomial here, r squared minus 2r plus 1 equals 0. Actually factors into an r minus 1 times r minus 1, so r equals 1 is a root twice. So e to the x is a solution, and x e to the x would be a solution. And then the particular solution to get the non-homogeneous part, since this is a polynomial here, a linear polynomial, I would expect the answer to be of the form ax plus b, and I could do a method of undetermined coefficients to figure out what a and b are. Okay, but anyway, so I have some idea that this is going to be an e to the x, an x e to the x, and then plus a linear polynomial for the solution to that equation. So here we go. And this time I'm not going to use summation notation. This is the way, up until very recently, I've done all of these. I just haven't been particularly fond of the notation of summations, and I just write them all out. So my y is going to look like this. I'm going to center at x equals 0. So then the derivative, just take the derivative of this thing, just like a polynomial, and the second derivative. And then what I want is, I want the second derivative minus 2 times the first derivative plus y equal to x. So here's the second derivative, minus 2 times the first derivative, plus the function itself, and that's supposed to equal x. So now I'm going to gather like terms. So I've got the constants, so I got a 2a2 and a minus 2a1 and an a0. Those are all the constant coefficients. Then the linear terms here, I got 3 times 2a3 minus 4a2 and then an a1. So there we go. I have a tendency to not actually multiply things together. Sorry, where am I? That's right here. Rather than saying 6a3, I leave it as 3 times 2a3 because it allows me to see patterns later. So anyway, things are generally not written, not multiplied out. They're written as factors so I can see them. So I'm just collecting all the constants, the linears, the quadratics, the cubics, and so on, and that's all supposed to equal x. The thing is, though, we're doing this because this is a big old infinite polynomial on the left-hand side, and this is a big old infinite polynomial on the right-hand side. Actually, it's a really little infinite polynomial because most of the coefficients here are 0, right? The one that's not 0 is the linear coefficient is a 1. So when I equate corresponding coefficients here, that the constant coefficient has to be 0. The linear coefficient has to be 1. This quadratic coefficient has to be 0. The cubic coefficient 0. Then all the rest of them are 0. Okay? So it's a little bit different than the homogeneous case where all of these were set equal to 0. In this case, one of them has to be a 1. Now it is feasible, although I'm not going to show an example of this, but if you had some function over here that was something other than a polynomial, like e to the x or sine or cosine, that you could actually write its Taylor series centered at the same place that you were centering your power series, and then equate each of the coefficients in this infinite polynomial to the one that you had over there. Right? And so you'd have a whole bunch of different coefficients here. Now it might be really difficult to solve, but then in which case you could at least work your way through the first few terms to get an idea of what the solution is going to look like. But in this case, there's only one and all the rest are zeros. So here we go. I can solve for, in each case I'm solving for the biggest of the a sub n's. So in this case I'm solving for a2, and this one I'll solve for a3 and a4. Right. So the first one says a2 is this, and then the second equation would say a3 is this, but that involves an a2, so I'm going to substitute what I got for a2 in for it and simplify it down to this. Notice that because there was a 1 right there, there's that one here. The difference that I want to point out is that this term, this A2, is written as a function of A0 and A1. Each term in there has an A0 or A1 in it. But this one here, because of that one, because of that non-homogeneous part, there's stuff that doesn't have an A0 or an A1 in it. There's this term of a 1, right? And then using that information, A4 is going to be, solving this one, move that over, divide by 4, divide by 3. So we get this, but we know A3 and we know A2, so plugging both of those in and simplifying, we get down to this thing, that 2 plus 4A1 minus 3A0 is 4 factorial. Likewise, I'm solving the next one for A5 and then the next one for A6. And at some point I say, do I recognize a pattern? And I do think that a pattern is emerging here. 2, 3, 4, 4 factorial, 3, 4, 5, 5 factorial, 4, 5, 6, 6 factorial. I expect the next one would probably be 5, 5, 6, 7, 7 factorial, right? That this would continue. I'm not completely sure. I would have to do it probably in the n's and the n plus 1s and the n plus 2s to see whether it really works or not. But for this demonstration, I think this is good enough. So I can see A0, A1x plus A2x squared plus A3x cubed and so on. And then I'm going to rearrange it and say what all has an A0. So I see a 1 A0 here. I see a minus a half A0. Oh, there's no x's, so there's a minus a half A0 x squared. There's that one. And there's a, what's this? The 2's cancel out and I get, or I guess, or not, there's a minus 2A0 over 2 times 3. So there's that, and just take all the A0s, then take all the A1s, and then take all the stuff that doesn't have either, because, right, there's a 1 over 6 here, and there's a 2 over 4 factorial there, and there's a 3 over 5 factorial there. So I've got, and each of those were times x to a power. So there's stuff with A0, there's stuff with A1s, and then there's stuff that doesn't have anything, either of those. So what I see here is this is very similar to what I was expecting for a solution, in that the two things that have these arbitrary coefficients out in front are the two independent solutions of the homogeneous equation, and then you have plus the particular solution. And this stuff right here does not depend on some variable. There's no constant out in front. This is just a particular function. Right? And this is what we would have called y sub p before. Now, it does not at all look like that is just a polynomial, right? That's certainly an infinite polynomial at this point. If I gave you this problem on a quiz or a test, I would expect that you stop right here, that you've done the work this far. I'm going to go a little bit further just to see that it is what I expect, because at the moment it doesn't look like what I expect, right? Solving the way we would originally have solved these things, I was expecting a constant times e to the x plus a constant times x e to the x plus a polynomial. And that's not at all what I'm seeing, because what I'm looking at here, this is not an e to the x. This is not, I mean, it certainly seems related to e to the x's, because I see like an x cubed over 3 factorial and x to the 4 over 4 factorial with all minuses in here, so it's like minus e to the x, but it's missing a linear term. Anyway, let's see if we can make it look right. So this is stuff that as a student I never would have been able to do. I don't expect you to be able to do it. This comes with some practice, having seen it done, getting used to how some of these patterns work. So what I'm going to do is I'm going to rewrite each of these things inside the parentheses. All right. This first one, this is all minuses here, right? This is a 1 minus, 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 and yet I'm going to rewrite it as a 1 plus x. There wasn't even an x there, so I better subtract x. And then I'm going to write this as a plus x squared over 2, but really it's minus x squared over 2. So I'm going to subtract 2x squared over 2's. Okay, so that would, this quadratic and that quadratic would be the same as that. And then I've got an x cubed over 3 factorial, adding it, but it really is supposed to be negative, so I've got to compensate by subtracting more of those. I'm essentially adding and subtracting the stuff that's here. So I'm adding all these positives in, and I'm subtracting them out, combining with the subtractions that are already there. Okay, essentially I'm adding 0. Okay. Likewise, down in here, what am I doing on the next one? So on the next one, all I'm going to do is factor out an x. I notice that there's an x in every term, and so I'm going to factor it out. And what's left there, actually this looks nice, because now this looks like my x e to the x, because that is the Taylor series or the Maclaurin series for e to the x. So I've got an x e to the x. What I'm trying to produce here is an e to the x, which I have, but then it's plus all or minus all this other stuff. Okay. Well, what is all that other stuff? Oh, I still need to look at what's happening on the inside of these parentheses. On the inside of these parentheses, I have added and subtracted a 2, and I've added and subtracted a 2x. And then, oh, that x squareds. I must have added and subtracted some x squareds over 2 factorial there. And then the negatives I want, yeah. So convince yourself that if you combine like terms down here, you get to what you started with. For instance, there's a minus 2x cubed over 3 factorial, and there's a plus 3x cubed over 3 factorial, which is that 1 that's there. And likewise, the 2 and the 4 give the 2 that's there, and the minus 2 and the 5. Anyway, just these add up to those that are in the parentheses. Okay, now, so this, on this part right here, I'm going to fact the stuff that's right here hiding behind my head is there's a factor of x in it. So I'm actually a minus x that's going to be factored out of that. Okay, so there was the e to the x that I already had. Now I have another minus x, and that looks like an e to the x as well. There's an x e to the x. And this last part, this part here, that was just the particular part of the solution here. This stuff right here is a couple of things going on. Notice that 2 divided by 2 factorial, the 2's cancel out, leaving just a 1 there. A 3 divided by 3 factorial, the 3's cancel out, leaving just a 2 times 1 there. A 4 divided by 4 factorial, the 4's cancel out, leaving a 3 factorial. So each of these is actually the n divided by n factorial is 1 over n minus 1 factorial. So each of these, what's going to happen is the factorials on the bottom are going to drop down by 1. And then I'm going to factor an x out of everything up to here, except that this 2x is going to be written as an x plus x. So I'm only factoring the x out of one of those x's, right? If you distribute this x back in here, whoops, wrong way. If I distribute this x back in, this is going to be x times 1, that's x times x, is the 2x, right? The x times x is x squared over 1, that's this one, and the x times x squared, this one right here, is x cubed over 2, that's this one, because the 3's cancel out, and likewise on down the line, okay? So the factorials are canceling with the numerators, and then an x is factored out of everything except for the 2x is written as an x times x, and the x is only factored out of one of those x's, because there's the other one. Okay, a lot of algebra done fast. But what I have now is I have a0 times, this is an e to the x, this is a minus x e to the x. This one, a1 times x e to the x. And then I have a minus 2, this is an e to the x. This is plus 2 plus x, and this is another e to the x, 2 plus x plus e to the x. So gathering some like terms here, I have an a0 e to the x, and I have a minus 2 e to the x. So that's an a0 minus 2 times e to the x. the x e to the x's, I have a minus a0, and I have an a1, and I have a 1. So all of that stuff is times x e to the x. And then I have a 2 plus x. And so my overall solution is some constant times e to the x plus some other constant times x e to the x plus this linear polynomial, which is what I expected, although it took an awful lot to get here. Right? Again, I would not expect you to be able to do this. I would expect you to get this far and then stop.